Hi, everybody. Welcome back. We're going to continue chapter 4, talking about how to name ionic compounds. And in this lecture, what we're going to do is we're going to do a bunch of practice naming ionic compounds. So we previously learned how to name binary ionic compounds, which is an ionic compound with two elements, a metal and a nonmetal. And we name those based on if the metal is a type 1 or a type 2 metal. And then we also talked about naming ionic compounds where we have a polyatomic ion. So we're going to do some practice problems with all of those. And then after this lecture, the next one will be naming hydrates, which isn't covered in your textbook. But when you do worksheet 2 as part of your lab assignments, you need to know how to name hydrates for that. And so we're going to cover that as an additional lecture at the end of this one. Okay, so when you're naming ionic compounds, we'll just review that real quick. The first step is to make sure that you are working with an ionic compound. So ionic compounds are going to have a cation bonding with an anion. And so you want to look for a metal with a nonmetal, and that's the most common type of ionic compound. So just always first make sure that you're working with an ionic compound, because if you have a covalent compound, which we're going to talk about in chapter 5, you name it using a different naming system. So you just want to make sure you're using the right system. So check that it's an ionic compound. Ionic compounds that just contain two elements, a metal and a nonmetal, are called binary ionic compounds. Those are a lot of the ones that we work with, but you can also have ionic compounds that contain polyatomic ions. So once you know it's an ionic compound, the next thing you do is figure out what type of ionic compound it is. Is it a type 1 ionic compound where the metal forms only one type of ion? Or is it a type 2 where the metal forms more than one type of ion, where the metal could have different charges depending on what it's bonded with? So to figure out type 1 versus type 2, it depends on where the metal is located on the periodic table. So the metals that are highlighted in blue here are all type 1 metals. They always have the same charge. So here, the metals that are highlighted in blue in the first column of the periodic table, starting with lithium, those metals always have a charge of +1. The next column over, starting with magnesium, those metals always have a charge of 2+. And then scandium always has a charge of 3+. And then moving across to the other side of the metals part of the periodic table, silver always has a charge of 1+. Zinc always has a charge of 2+. And aluminum always has a charge of 3+. So these are your type 1 metals. They always have the same charge, which is indicated here on this periodic table. All of the other metals on the periodic table make type 2 ionic compounds, meaning that the metal could have a couple different charges depending on what it's bonded with. And so when we name ionic compounds for the type 1 metals, the ones shown in blue here, because we know their charge is always the same, we don't have to include the charge as part of the name because it's always the same. But for the type 2 metals, because the charge could change, we have to incorporate it into the name to make sure we properly name the compound. So when you name a type 1 metal bonded with one other element, how you name it is you name the cation first, which is the metal, and then you name the base of the anion, the nonmetal part, with an IDE ending. If you have a type 2 metal, it's the same naming convention, except for you have to insert the charge of the metal in Roman numerals inside parentheses. Again, because type 2 metals could have different charges depending on what they're bonded with, we have to include their charge in the name so we know what it is. So when you name an ionic compound that has a type 2 metal, you put the name of the metal first, the cation, and then right next to that in parentheses, using Roman numerals, you put the charge of that metal. So if your metal has a charge of 2+, you put the Roman numeral 2 in parentheses right next to the name of the metal. And then you put the base name of the anion with an IDE ending. And then if we have a polyatomic ion, you just insert the name of the polyatomic ion wherever it occurs. So if your polyatomic ion is a cation, is taking the place of the metal, then you insert the name of the polyatomic cation in place of the metal. And if your polyatomic ion is an anion, negatively charged, it would be taking the place of the nonmetal, and you just put the name of the polyatomic ion in place of the nonmetal. And you don't have to change the name of the polyatomic ion. You don't add any Roman numerals to it and you don't add an IDE ending. It just stays whatever the polyatomic ion name is. That's how you put it in the name of the compound. We do that for polyatomic ions because polyatomic ions always have the same charge. So we don't have to change the name or add Roman numerals for a polyatomic because its charge is always the same. Okay, so let's practice naming some. We're going to go from formulas to names and then from names to formulas. So let's start with type 1 metals. So metals that have a fixed known charge. So if we start with the formula KCl, to name this, we name the metal, and then we name the non-metal with an IDE ending. So our metal is potassium. And the non-metal is chlorine. So the base of that is chlor. And then we add that IDE ending, potassium chloride. Okay, next one, we have CaS. Ca is calcium. So we just write the name of the metal, calcium. And because calcium is a type 1 metal, we know it always has a charge of 2+. We don't have to include the charge in the name because we know it's always going to be 2+. So now we put the name of the non-metal, which is sulfur, but we change it so it has an IDE ending. So it becomes sulfide. Next one, going from a name to a formula. For magnesium bromide, we know that our cation is magnesium. We always put the cation first in the formula as well as in the name. And magnesium always has a charge of 2+. It's a type 1 metal, so it's always going to be 2+. And magnesium is bonded ionically with bromine as an ion. That's why it's named bromide. So we put the symbol for bromine, and bromine always has a charge of 1-. So now to make sure that we write the formula correctly, we have to make sure that overall our ionic compound has a charge of 0 or is charge neutral overall. So since our magnesium has a charge of 2+, and our bromine has a charge of 1-, if we added up these charges right now, we'd get an overall charge of 1+. We take +2 plus -1, it equals 1+. So this isn't the correct formula. We're going to have to add some subscripts so that our number of ions and the associated charges then add up to 0. So you can use what's called the crisscross method, where we're going to have 1 magnesium and we're going to have 2 bromide ions. So if we get rid of the extra text that I put in here, get rid of those arrows. I'm just accidentally getting rid of everything. Here we go. We get magnesium, Br, and we ended up with the 2 here. And now if we check our charges to make sure they add up to 0, for magnesium, it has a charge of 2+ times 1 atom of that equals a total charge of 2+ from the magnesium. And for the bromine, the bromide ion has a charge of 1-, and we have 2 atoms of that. So a total negative charge of 2-, and so those add up to 0, which checks out because ionic compounds have to have charge neutrality, meaning that the sums of their positive and negative charges have to add up to 0. Okay, our next one, barium oxide. So you always write the symbol for the cation first, which is barium. So Ba. Barium is in column 2 of the periodic table, group 2A, so it has a charge of 2+. And then oxide is the ion of oxygen, so it's O. And oxygen as an ion, oxide, has a charge of 2-. It's in column 16 or group 6A of the periodic table. So when oxygen forms an ion, it's going to gain 2 electrons to get to 8, the closest noble gas, which is neon. So when it gains 2 electrons, it's going to make an ion with a charge of 2-. So if we did the crisscross method on this, we would get 2 and 2. But when you write formulas for ionic compounds, you want them to be in the lowest common factor that they can be. So since we have 2 bariums and 2 oxygens, the lowest common factor is just one of each of those. So you just get barium oxide with 1 atom of each ion. Okay, let's do some more. Let's try some with type 2 metals. So again, type 2 metals are the metals in the middle of the periodic table, where their charges could be different depending on what they're bonded with. So when we write the names for type 2 metals, the name is always going to have a Roman numeral that shows the charge on the metal ion. Type 1 metals should never have Roman numerals because we always know their charge, and type 2 metals will always have Roman numerals because we need to specify what charge state they're in. Okay, so here we go. Our first formula is Fe2O3. So Fe is iron. And we're going to have to specify the charge on that iron inside these parentheses in Roman numerals, but I'm going to leave that blank for now. And then O is oxide. It's the ion of oxygen. So it's the root of oxygen, OX, with the IDE ending. So now our job is to figure out the charge of the iron based on what it's bonded to. So we know overall this compound with 2 iron atoms and 3 oxygens needs to have a net charge of 0. So if we draw a little chart here, we have iron, we have 2 atoms of iron times whatever charge it is, plus for oxygen, we have 3 atoms of oxygen times each oxide has a charge of -2. So that means altogether the oxygens are providing a charge of -6. And if these charges have to add up to 0, that means the iron must be providing an overall charge of +6. So that the positive charges plus the negative charges add up to 0. So if iron is supplying a charge of +6 altogether, and there's 2 atoms of iron, that means each atom has to have a charge of +3. So that when you take 2 atoms times a charge of +3 each, you get a total positive charge of +6. So that means we're dealing with iron 3 oxide. The Roman numeral shows us the charge on the iron. Okay, next one, COCl2. C with a lowercase o next to it is cobalt. It's a type 2 metal, so it's going to need parentheses with Roman numerals inside to show us the charge on the cobalt. And then the anion in this case is the ion of chlorine, so that's chloride. So if we do some math here, we have cobalt, not calcium, cobalt. We have 1 atom of cobalt times whatever its charge is. And for chlorine, we have 2 atoms of chlorine times each chloride, when it forms an ion, has a charge of -1. So the total charge from the chlorides is -2. That means that the total charge contribution from the cobalt has to be 2+ altogether so that they add up to 0. Which means that since we only have 1 atom of cobalt, that 1 atom of cobalt must have a charge of 2+. 1 atom times a charge of 2+ equals 2+ altogether from the cations. When you add that together with the total charge from the anions, you get 0, which is what we need for an ionic compound to be charge neutral. So this is cobalt 2 chloride. Okay, let's go from the name back to the formula. So we have iron 2 sulfide. So Fe is going to go first in the formula. The cation always comes first. And this is iron 2. So this iron atom is going to have a charge of 2+. And then sulfide is S. It's an ion of sulfur. And sulfur ions always make a charge of 2-. So now if we add up the charges, we have iron, certain number of iron atoms times 2 plus, certain number of sulfur atoms times 2 minus. If we make both of these 1, you get a total charge of 2 plus a total anion charge of 2 minus equals 0. So we just need 1 atom of each. So our final formula ends up being FeS for iron 2 sulfide. Okay, next one, we have tin 4 oxide. So tin is Sn. We know it has a charge of 4 plus on every tin atom or tin ion that's in the formula. And then our anion is oxide, O, and each oxygen has a charge of 2 minus. So to figure out how many of each of these atoms we need to add any subscripts. We can do the math. So we have tin, however number of atoms we need, times 4 plus, oxygen, however number of atoms we need, times 2 minus. If we pencil in 1 of each of these, we get 4 plus and 2 minus. So in order to get these so that they add up to 0, we're going to end up needing 2 atoms of oxygen so that we get a total negative charge of 4 minus and they add up to 0. So our formula ends up being SnO2. And again, when you write formulas, you don't include the charges. Those are just there to remind us what we're writing. So our final formula is SnO2. It takes 1 atom of tin with a charge of 4 plus 2 ions of oxygen, each with a charge of 2 minus, to make a charge neutral ionic compound. Okay, let's do some more type 2 metals. I think these are the trickiest sometimes to figure out because you have to take the Roman numerals into account. Okay, so next we have CuBr. So we have copper. Copper is a type 2 metal, so we're going to have some Roman numerals to tell us the charge on the copper. And then we have bromine, but because it's an ion, it's in an ionic compound, we change it to bromide with the IDE ending. So we have copper, some Roman numeral, bromide is going to be our final name. So to figure out the Roman numeral, we have to figure out the charge on the copper. So right now we have 1 atom of copper times whatever its charge is. And for bromide, we have 1 atom of bromide times each atom has a charge of 1 minus equals 1 minus. And these two need to add up to 0, whatever the sum of the positive charges is. So for this to add up to 0, the sum of the positive charges has to be 1 plus, which means 1 copper atom has to have a charge of 1 plus. So this is copper 1. Okay, next one. FeS. We just did this one on the last slide, except for we took it from the name to the formula. So our metal is iron. It's a type 2 metal. It's in the middle of the periodic table. It's not one of those special type 1s, so it's going to get Roman numerals. And then our anion is the ion of sulfur, so we call that sulfide. And now to figure out the charge on the iron, we need to figure out what charge the iron atoms need to be so that the sum of the cations plus the sum of the anion charges add up to 0. So we have 1 iron atom times its charge. And for sulfur, we have 1 sulfur atom or ion times the charge of -2 for sulfur equals 2 minus. Those two have to add up to 0. So in order for 2 minus to add with something to make 0, you have to add it with 2 plus. And since there's only one iron atom, that one iron atom has to have a charge of 2+. So it's iron 2 sulfide. Okay, next one. We have lead 4 oxide. So our first chemical symbol is going to be the symbol for lead. And we know this lead has a charge of 4+ from the Roman numeral. And then oxide, the symbol for oxide is O. And I'm going to leave blanks here in case we need to fill in any subscripts. So our charge in our lead is 4+. The charge on a single oxide is 2-. So you can kind of use the crisscross method here if you want. You just have to reduce it to the lowest common factor. So if we do the crisscross method, you get 2 here and 4 here. But ionic compounds need to be written with formulas that are the lowest common factor for that formula. So this formula right now has Pb2O4. If you divide everything by 2, because everything is divisible by 2, then you end up with the correct formula, which is PbO2. And if we want to check the math on that, we have lead. We have one of those times 4+. And for oxygen, we have 2 atoms of those times 2- each. 4+, 4-. If you add that up, you get 0. So just remember, if you take the shortcut of doing the crisscross method rather than working out the math, that once you criss and cross both the numbers, you need to reduce it to the lowest common factor. Okay. Let's do the next one. So we have iron 3 nitride. So we know our first chemical symbol is going to be Fe for the iron, and it has a charge of 3+. And then nitride is the ion of nitrogen. And nitrogen makes 3- ions. So if you wanted to try the crisscross method in this to quickly figure it out, you'd get 3 and 3. And when you reduce that to the lowest common factor, they can both be divided by 3. So you get Fe and iron 3 nitride. We can, of course, always check the math. So for iron, we have 1 atom of iron times a charge of 3+ equals 3+ for the irons. And for nitrogen, we have 1 atom of nitrogen times a charge of 3- equals 3-. And when we add those up, you get 0. So it works out. Okay, let's move on to some more. Okay, let's do these ones. These are with polyatomic ions. So in this case, we're given the cation for our ionic compound, and we're given the anion. And the cation or the anion, or in the case of this last example, both contain a polyatomic ion. So we have to come up with the ionic compound formula that results in the net charge of the formula being 0. So we make a neutral ionic compound, and then we'll name the compound after we come up with the formula. So with the cation of sodium, it has a charge of +1. And the anion OH is a polyatomic anion, that's hydroxide. And it has a charge of 1-. So we end up with NaOH as our formula. And we can check, we have a charge of 1+, a charge of 1- from the hydroxide. So 1 unit of each of those, 1 sodium and 1 hydroxide, adds up to 0, which is what we want to make sure our ionic compound is charge neutral. So NaOH, and then to name this, we name it like a regular type 1 ionic compound, where you name the metal first, sodium. And because sodium is a type 1 metal, we don't need any parentheses with Roman numerals. And then in place of the non-metal, we just name whatever the anion is. And in this case, the polyatomic anion is hydroxide. So this is called sodium hydroxide. Okay, next one. We have magnesium 2 plus NO3 1 minus. NO3 is nitrate. It's a polyatomic ion. So we need to come up with an ionic compound formula so that we have the right number of magnesiums and nitrates so that the overall charge of the compound is 0. So if you do crossing the charges, you get a 2 for the number of nitrates and a 1 for the number of magnesiums. So that would give us the formula Mg NO3, and we need 2 of these. So we have to put parentheses around the nitrate followed by the 2 to show that we have 2 of these nitrates as a unit. If we forgot to put the parentheses, it'd look like 32 oxygens, which would be incorrect. So when you're showing that you have more than one polyatomic ion, you put parentheses around the polyatomic ion that you have more than one of. And now to name this, magnesium is a type 1 metal, so we just name the metal. No Roman numerals are needed, but if it were a type 2 metal, you'd name the type 2 metal just like you always do. You'd put the name of the metal and then the Roman numerals with the parentheses with the Roman numerals to show the charge. So our metal is magnesium, and then our anion is nitrate. And that's it. You don't have to change the name of the polyatomic ion at all. We know that nitrate, it always has a charge of 1 minus. Therefore, in order for this compound to be charge neutral, there must be 2 nitrates with every 1 magnesium to give us a formula of MgNO3 Okay, last one. We have 2 polyatomics. We have ammonium and this should be NH4 plus. There's an error on that slide, NH4 plus with sulfate SO4 2 minus. So we still need to write the formula so that overall this ionic compound has a cation and an anion. So the overall charge of this ionic compound adds up to 0. So you can still use the crisscross method on this with 2 polyatomics. Sulfate has a charge of 2 minus. So it's going to take 2 ammoniums to make a total positive charge of 2 plus. And it will just take 1 sulfate ion with the charge of 2 minus. So if we have NH4, SO4, that's our formula for this compound. And again, that's because, 2 of those, by taking this charge and using the crisscross method to bring it down. And if we check that the math works out for this, each ammonium has a charge of 1 plus times 2 of them equals a total positive charge of 2 plus. And for the sulfates, each sulfate has a charge of 2 minus, and we have 1 of those equals a total negative charge of 2 minus. So they add up to 0. And then to write the name for this compound, you name the cation ammonium, and then you name the anion polyatomic ion sulfate. Okay, so we're next going to talk about naming hydrates. Hydrates are a special type of ionic compound. Your textbook doesn't really go into hydrates very much, but in the lab, you're going to be talking about hydrates coming up in experiment 4. So we're going to cover how to name hydrates here, and you'll also need this to complete worksheet 2. So some ionic compounds, which we call hydrates, contain a specific number of water molecules associated with each formula unit of the ionic compound. it's kind of like the water molecules are not chemically bonded with like a ionic bond to the ionic compound, but they're very closely associated. They kind of stick to the ionic compound. And so to name a hydrate, you name the ionic compound as usual, and then you put a dot between the ionic compound name and the water molecules. And you use a prefix to show how many water molecules there are, followed by the word hydrate. So if your ionic compound has 2 water molecules associated with every formula unit of the ionic compound, you'd use the prefix di to mean 2. And so you'd end up with your ionic compound name, a dot, and then dihydrate. If there were 4 water molecules associated with each formula unit of your ionic compound, you'd name your ionic compound, and then you'd put a dot, which shows that the water molecules are a hydrate of that ionic compound. So you put a dot, and then you put tetrahydrate. To show that there's 4 H2Os, water molecules associated with that ionic compound. So let's do a couple of examples on a whiteboard. We'll take the formula BaCl2 6H2O and turn it into the name of the hydrate. And then we'll take the name copper 2 sulfate pentahydrate and turn it into the formula. Okay, so our first one, we're going to take BaCl2 6H2O and go from the formula to the name. So first thing, this first part is the ionic compound. This part is the hydrate. So we're going to name the ionic compound like we would any other ionic compound, and then we'll add in the part that reflects the number of water molecules attached to that ionic compound. So barium is a type 1 metal, so we're going to name it barium. No Roman numerals because it's type 1. We know that each barium has a charge of 2+. And then chloride. And that's the ionic compound. And then for the hydrate part, there's 6 water molecules for every 1 barium chloride. So we're going to name that hexahydrate. Hexa means 6. And then hydrate means H2O. Okay, our second example for hydrates was taking the name copper 2 sulfate pentahydrate and taking that from a name to a formula. So we're going to dissect this again. We've got the ionic compound, and we've got our number of waters attached, number of H2Os. And that's probably a better way to put it. It's the number of H2Os. So we're going to take the ionic compound part and figure out the formula for this ionic compound. And then we're going to put a dot between the ionic compound, and then we'll use a number in H2O to show the number of water molecules attached. So copper 2 sulfate, we know we're going to have copper, and then we're going to have sulfate. Sulfate has a charge of 2-. And because this is copper 2, it has a charge of 2+. So if we cross these, we get 2 sulfates and 2 coppers. And the lowest common factor between these is 1. You can divide everything by 2. So that would go away, and that would go away. and you end up with just copper 2 sulfate. I'm going to move these together so they don't look like they're two separate things. So that's copper 2 sulfate. Now we need to add in the waters. So to do that, you put a big dot. And then penta means 5 from the chart, and hydrate means H2O. So 5H2O. So that's how you write the formula for copper 2 sulfate pentahydrate. It's pretty cool, right? It's like a big, long chemistry name, which before today might have looked a little scary or you didn't know what it means. And now you can dissect it little by little to write the formula for the ionic compound part, copper 2 sulfate. And pentahydrate means that that copper 2 sulfate has 5 molecules of water associated with each one formula unit of the ionic compound. So again, here's this prefix table. This is also in worksheet 2, and you'll be using this as you complete worksheet 2, as well as when we do experiment 4 in the lab. And I just want to point out the prefix hemi, which means 1/2. So with this prefix hemi, meaning 1/2, do you think there can actually chemically be a half a water molecule attached to a hydrate? Give you a second to think through that one. You can't have a half of a water molecule. A molecule is one unit of a pure substance, a molecule. So you can't split up a molecule and have it still retain the identity of that substance. So you can't have a half a molecule of water. What the hemi means is that for every one formula unit, mathematically, you have a half of molecule of water, but in reality, you actually have double of everything that the formula shows. So for example, if we have something like the formula calcium chloride hemihydrate, what this actually means is that what you would have in real life is because you can't have a half a molecule. Can't in reality have half a molecule. So what that really means is in real life, everything is multiplied by 2. So how this compound is actually found is 2 calcium chlorides and really like 1 H2O. That for every 2 formula units of calcium chloride, you find 1 molecule of water. But we always write hydrates so that the ionic compound is in the lowest possible factor, which means that this would be a 1 instead of a 2. So we have to divide everything by 2, which is how we divide by 2, which is how we end up with calcium chloride 1/2 H2O. But really what's happening is that for every 2 formula units of calcium chloride, we have 1 molecule of water associated with those 2 formula units of calcium chloride. You can't really have a half a molecule of water. It's just the convention of writing these that we keep the ionic compound as the lowest whole number possible, which means that we end up with the hemi water. But in reality, there's 1 whole molecule of water because you can't split up a molecule and have it still be the same identity, still have it still be water in this case. So you have 1 molecule of water with every 2 formula units of calcium chloride. So let's do some more practice with polyatomic ions and hydrates and kind of mix everything up here. Okay, our first one, we've got COCl2 with a big dot, 6H2O. So this is a hydrate. We've got our ionic compound part in the front, our formula unit of the ionic compound, and then we've got our number of water molecules associated with that at the end. So we're going to name the front part first, the ionic compound. So we have cobalt. And cobalt is a type 2 metal, so we're going to need some parentheses with that. And it's bonded with chloride. And let's figure out this front part first. So cobalt is bonded with chloride, and each chloride has a charge of 1-. And there's 2 of them, so times 2 equals the total negative charge is 2-. Let's make that bigger. So each chloride is 1-. We have 2 of them equals 2- from the chlorines. So that means the cobalt must be 2+. Because there's only 1 atom of cobalt, that 1 atom of cobalt must have a charge of 2+, so that the charges overall add up to 0. -2 plus +2 equals 0. So we have cobalt 2 chloride. And then for the hydrate part, we have 6 water molecules. So the prefix for 6 is hexa, and then hydrate. Okay, let's take this next one, a hydrate name, and turn it back into the formula. So we have magnesium sulfate heptahydrate. So we're going to start out with MgSO4. Magnesium has a charge of 2+. Sulfate polyatomic ion has a charge of 2-. So we don't need to add any subscripts here to get this compound to be charge neutral. It's charge neutral as written, magnesium sulfate. So the next part is to take care of the water molecules. Hepta means 7. So we have a big dot and then 7H2O. Okay, next one, we have the ionic compound formed between aluminum and sulfate. So aluminum is a type 1 metal. It always has a charge of 3+. Sulfate is a polyatomic ion. It has a charge of 2- always. So we can check 3+ times 2 atoms equals 6+ from the aluminum, and sulfate, we have 2- times 3 of those equals 6-. So the formula is correct. It adds up to 0. So now we just have to write the name. The metal goes first, aluminum. We don't need any Roman numerals because aluminum is a type 1 metal. It's always going to be +3. So now we just add in the name of the polyatomic ion, sulfate. Okay, last one. We have the name. It's got put in the wrong spot. We have the formula MnCO32. So let's write the name over here in this blank spot. So Mn is manganese. Make sure you don't get it confused with magnesium. Magnesium is Mg. Magnesium is a type 1 metal. It always has a charge of 2+, but manganese is a type 2 metal because it's in the middle of the periodic table. It's not one of the metals that has the defined charge. So we have manganese. And we're going to need some Roman numerals with manganese to show what charge it is. And then it's bonded with CO3, which is carbonate, which is a polyatomic ion that has a charge of 2-. So we have a charge of 2-, and we have 2 of those. So if we do our math, we have MnCO3. We have one manganese ion times, we don't know what its charge is. And we have two carbonates, and they each have a charge of -2. So the total negative charge is 4 minus. They have to add up to 0, which means our manganese must have a total charge of 4 plus. And since there's only one of those atoms, that one atom or ion must have a charge of 4 plus. So we're dealing with manganese 4. And then our anion is carbonate. And that's how you write that one. Okay, so start working on worksheet 2, which is all about nomenclature, naming compounds. Start with pages 1, 2, 7, 8, and 9. There are 12 pages total, but if you start with these pages, these are the pages that focus just on ionic compounds. And we've covered everything you need to know to name the ionic compounds now. In chapter 5, which is next, we're going to go over covalent bonding and how to name and write formulas for covalent, also called molecular compounds, as well as acids. So we'll cover the rest of what you need to know to do worksheet 2 in chapter 5 towards the end of chapter 5. But worksheet 2 is a big one. Like I said, it's I think it's about 12 pages. So you want to get the ionic compound naming done with right away so that when worksheet 2 is due, you just have to finish up the covalent compounds and you don't have to do the whole thing at once, because it does get kind of long if you try to do the whole thing at once. Okay, that's it. That's the end of chapter 4. Feel free to reach out if you have any questions, and I'll see you next time when we talk about chapter 5. Thanks, everybody.